nerve pellet coming out was. What are the conditions that we know? Yes. Okay, so that's the X final, right? So X final is, and for fun, let's just say 5 meters. Okay? Just for simplicity. What else do we know? Yes. Okay, so the height initial, we'll call that Y. We'll call that YI, was 1 meter. Okay, what else do we know? Yes. Okay, we know that gravity is acting on it, so we use G is equal, we'll just say A is equal to minus 9.8 meters per second. And for this calculation, it's really been one to consider, let's just say 10 meters per second squared. Okay, what else do we know? Yeah. Okay, Y final is 0. What else do we know? Okay, so A, so we'll just put this A of Y is minus 10 and A of X is equal to 0. We know some other things to go on too. Good, thank you. Yes? Okay, so the initial, so X0, we said that's 0. Okay, good. What else do we know? Yes? Okay, mass is 1 gram. You won't need to worry about that now. When we start dealing with forces, that will become important. Okay? Anything else? What was the initial velocity in the y direction? Okay, 0. So V0y is 0. What don't we know? Yes? Okay, we don't know time. What else don't we know? Yes? Okay, we don't know V0f. We have enough information to solve this. How can we find time? Yes? Okay, and so good. So, but we're just so what he's saying is basically we can take the equation. We have this y final is equal to y final is equal to y initial plus v0y times. So let me just write that down. You said x, but I know what you meant. You meant y. So we have some y final is equal to y initial plus v0y times t minus 1/2 g t squared. All right? What is y initial? Y initial is 1, right? 1 meter. What's v0y? 0. Minus 1/2 times 10 times t squared. Well, okay, I'll keep it as g. G t squared. Now, the nice thing about this is that v0y was 0, so we don't need to worry about that. Okay, so we're going to have, this is 1 meter, and instead of calling it 1 meter right now, I'm just going to say this is y0. So let's solve for t, right? If what I have here is 0 is equal to y0 minus 1/2 gt squared. So if I take 1/2 gt squared is equal to y0, then t is equal to 2 y0 over g square root. Okay? Now, 2y0, y0 is 1 meter, so I have 2 times 1 divided by 10. So I have 2 divided by 10, so I have the square root of 1 over 5. Sorry. Yeah. Sorry. 5, and this is going to be in seconds. That's about 22. So 0, sorry, 0.4 seconds. I think that's about right. So 1 over root 5, so the square root of 5 is like 2.2, somewhere in there, a little bit less, 0.15 or something like that. But we'll just round. And so if I have 1 over that, I'm just going to say that's a little bit less than, so if this is 1 over 4, right, this would just be 1/2. And so I would get a 1/2 of a second, but this is a little bit less than a 1/2 second. I'm just saying 0.4 seconds. Okay, now, so that's how long it was in the air. How are we going to find V0, V0x? Sorry?
X is equal to VOX times T.
Okay. So x final minus x initial is equal to V0x times t. Do we have acceleration? No. Okay, good. Do we have t? Okay, good. So we can just say this is 0. So we see that x final is equal to, so solving for V0x, we just get this as x final all over 0.4 seconds. So basically, I'm just going to multiply. When I have a 0.4 in the denominator, that's basically multiplying by the square root of 5 in the numerator. And so I have 5 times the square root of 5 meters per second. That makes sense? Okay, so I did a little bit of, right? I could have just called this 1 over root 5, which is 0.4 seconds. But 0.4 seconds is where we got this originally from, and so I just replaced that with 1 over root 5, but that's just bringing the root 5 into the numerator, and so I get 5 root 5 meters per second. Okay, so at that particular, knowing that velocity, then I can go back and roughly calculate the force that was acting on it, knowing the length of the pipe. And once I know the force, then I can determine the pressure inside of the chamber. And that's a rough calculation, and we'll show that these are fairly good agreement with what we expect. So this is how you can. There are many different ways to measure projectile velocities, and simply just looking at distances is one of them. So another thing that we were talking about last time is that it's a very good approximation if you have a very massive object moving at slow speeds, and once you have a range. Now, this is actually not a good. This would be better. I need some assistance. Anyone want to come down and help out? No? Come on, someone's ready. Okay, here we go. You never know what you're getting into, so I can understand. Okay. So, let's move this over here. Now, what we were saying earlier is that the range, to calculate the maximum range, you have to have the same height. Okay, so I want you to catch this ball. Make sure it doesn't hit the table. So you have to actually have the final height be equal to the initial height in order to make the assumptions that were made. Thank you. Okay, so now if I lower this down. Okay, so just move that plate until it goes roughly. Okay, so perfect. Okay, so we saw where that landed. It's about right. Okay, good. Got it. All right. Now, so what's going to happen if I raise it up to 90 degrees? How far is it going to go? Okay, well, won't go very far. So, how about if I do it went further. Oops. Okay, so let's see that. Let's go back towards that. Yeah, they're about the same. Okay. Now let's go down to 25. So you can see that it's roughly correct. I think there's quite a bit of uncertainty on this spring about each release is a little bit uncertain. But, okay, great. Thank you. You want to do push-ups? Okay. So later on this semester, I will have some of you do push-ups. Okay, so now I want to do a quick demonstration of parabolic trajectory. So here we have an air table, and on this air table we're just going to move a puck, and what we're going to do is release this puck and show that it has a parabolic trajectory. Okay, so this air puck there's actually still quite a bit of friction here, as can be seen. There's too much friction on these tables. Then air comes out here to make it have essentially zero. But the important part I wanted you to see is that this actually undergoes a parabolic trajectory here. But this table still has too much friction, so you can't see what's happening there. So it's supposed to have more pressure coming down there. Okay, so now, any questions about two-dimensional trajectories? Everyone's good? Okay, so now let's move on to the next section, which is uniform circular motion. Okay, so with uniform circular motion, what we're going to assume is that there is something, when I say uniform, that means its speed is constant, that it's going around at a constant speed. Is the velocity constant? No, why is that? Okay, the direction is constantly changing. So if the velocity is changing, then is there an acceleration? Yes, and what is this acceleration called? Sorry? Centripetal acceleration, which is a center-seeking force. Now, how many of you ever been on a merry-go-round that got going really quickly? I have. I was traumatized as a young man. I was about 6 years old, and I remember holding on to a merry-go-round, and it felt like my body was straight out. Of course, it wasn't, but I was going around pretty quickly, and I wasn't enjoying it. It didn't feel like it was a center-seeking force. force, because when I let go of that, I flew away pretty fast, right? Because it felt like it was pushing on me really hard. Why is this interesting? Last night I was playing with my boys in the gym, and we were doing one of those, they had one of these little piano dollies, and I was spinning them around on one of these piano dollies. And they were just going around in circles, having a great time. Felt like they were being pushed away. Yeah. Okay, so this is your thinking along the right line. What actually kept me going in circular motion was the force that I was exerting to hold on, right? Or in that particular case, it was I had a big long PVC pipe with my boys. They were holding on to that pipe, right? They were exerting the force that was keeping them, allowing them to undergo circular motion. Okay, so in this, what we can think about is what is the force necessary to keep it going in circular motion, right? And that's what you can think about as being this centripetal motion. So I'm going to, maybe I should draw a little bit bigger. This is kind of important. Okay, so I'm going to have a circle here. And I want to emphasize this is uniform circular motion. If I draw the displacement vector relative to the origin, so we're just going to assume that it's going around the origin, okay, and it has a constant speed as it's going around. If I look at the displacement vector, it looks like this. So we can think about the displacement vector as coming from the origin and going out to where that particle is in this uniform circular motion. Now, which direction is the velocity? Well, it can be this way or it can be this way. For the sake of this class, we're just going to assume it's this way. Now, what do we know about the angle between the displacement vector and the radius vector? Sorry, between the radius vector or this displacement vector relative to the origin and the velocity vector. They're at 90 degrees. If it's circular motion, then the velocity is tangent to the circle. Whereas the radius, or that, I'm calling it r, that vector, this displacement vector, goes from the origin out to that edge. So we're going to say, so this, for uniform circular motion, this is 90 degrees. Okay? So let's break this up now. We're going to call this angle theta. And we're going to say, what is the component of r along the x-axis? Right? We can break this up into its components. As two components, we'll call this one x, p, and it's just because we're calling this as point P up here. And we're going to call this y, p. Everybody so good with that? Okay, so now, if this is 90 degrees right here, this is, right, we're going to go back to geometry. Okay. What is this angle right here? Okay, right, we know that the sum of these three angles has to be 180 degrees. We know that this is 90 degrees here, so we know that this has to be 180 minus 90 minus theta. Right, so we get 90 minus theta up here. Okay, we have 90 minus theta plus 90. So what does that have to be equal to? Theta. Right? So this is theta up here as well. Okay, so now if we look at this in its coordinate system, okay, I'm sorry, this is going to be a tight picture. There's a lot happening here. But this is my velocity vector coming out here. What is the magnitude of the velocity in the y direction? Which is this. So if I look at R, let me draw it up here. I'm saying R is equal to x p I hat plus y p j hat, right? And I can say what xp is. Xp is just the cosine of theta times R. Plus yp. Yp is just the R times the, oops, sorry, that's the I hat. Plus R times the sine of theta j hat. Okay? Now, what is the velocity? So the velocity vector, right? If this is theta right here, then this is v of y. It's the amount going in this direction. What is vy? Sorry? Okay, in this particular case, theta is this angle, so it would be v cosine theta, right? Oops, sorry. That's velocity of y. Here we get minus, for the x, I get minus v. I get minus v times the sine of theta, I hat, plus v times cosine of theta j hat. And all I did was I said this is theta right here, and so the adjacent is this term. That's going to be the velocity in the y direction. And this is the velocity in the x direction. But now this is going to be the opposite, so I'm just going to get, but it's in the negative direction, so I'm going to get minus v times the sine of theta, and I'm going to get plus v times the cosine of theta. And that's all I did here, breaking this velocity vector into components. Okay? All right. Now, we're going to use a little bit of trickery here. Not necessarily trickery, but what we want to be able to do is I want to be able to take dv dt. I want to take the derivative of the velocity with respect to time. Now, is v changing or is it constant? The magnitude of v is constant, right? That's just it's undergoing circular motion. The reason why we broke it up like this is so this is not changing, but the angle is changing as a function of time. Okay. So the angle is changing as a function of time. And this is constant, and the angle is changing as a constant function of time. So if I look at this, what I can say is the sine of theta, going back up to here, the sine of theta here is equal to the opposite over the hypotenuse. And so I can say that this is equal to minus v. I just use this yp over r. And this is I hat plus v. And then cosine of theta is just going to be xp over r. Now, if I take the derivative of that, here, I'll go over here. I don't have to erase this. So the acceleration is simply the time derivative. The acceleration is simply the time derivative of the velocity. Now, v we said is constant. R is constant. That's just the magnitude of the length of the displacement vector. But is yp changing? Yes. Is xp changing? And what you can think about is it's just the component of that vector as this is undergoing circular motion. And as it's undergoing circular motion, this is changing and this is changing. But v and r aren't changing. Those are just the magnitude of the velocity and the magnitude of the displacement or the radius vector. Okay, so now if I say A is equal to dv dt, then I'm going to get that this is minus v vy, right? If I take derivative of yp with respect to t, what is that? That's vy, right? This is vy. So I'm going to get Vy over r I hat plus Vx over r j hat. Okay, now we do it again. Yes? Oh yeah, okay. So
to my mind, it just seems like it would be v times cosine theta plus.
So let's look at our velocity vector. When I look at, here's my velocity vector here, right? Okay, and here's the angle, theta here.
Could you just have pi over 2 over 490 plus theta?
So I could, so the way to think about it, all we need to remember is it moving in the positive x direction or in the negative x direction? And this, what we're doing is we're saying we can see from here that the velocity has a component that's negative in this direction. So for a positive angle, theta, I need to have a negative value. So that's why I put a...
will that not change
Well, we just need to remember that when we're taking the radius vector, we're taking it with respect to this, with respect to the x-axis, and we do the velocity vector, we're taking it with respect to the y-axis. So if you just remember that, then everything will be consistent. Okay? So, now, Vy is something that we already know, right? We've already determined what Vy is. It is just V times the cosine of theta. So we get minus V squared over r cosine of theta. And I hat minus Vx, as we were saying, is minus V times the sine of theta. Right? Because here's Vx pointing out here, and here's Vy pointing up here, right? So Vx is in this direction, so it's going to be minus, because it's in the negative x direction, times the sine of the angle, because it's the opposite over here, times the magnitude of V. So we get V minus V squared sine theta over r j hat. Now, if I were to look at all of these vectors, which direction is this going? Look at this vector right here. You'll notice that this is a cosine theta, and this is a cosine theta. This is a sine theta, and this is a sine theta. But notice that this is a plus sign, and a plus sign, and this is a minus sign, and a minus sign. Yeah, so it's pointing, the acceleration is pointing back at the origin. Okay, so and you can just simply see that because the minus signs mean the vector, it's taking the opposite of the vector pointing out, and it's pointing back in. Okay? So, the acceleration vector is pointing towards the center. The displacement vector, or the radius vector, is pointing away from the center, and the velocity vector is pointing tangent to the circle. Okay, so this is the idea behind uniform circular motion. Now, if I want to find the magnitude of A, how do I do that? Yes? Okay, good. Okay, so I have V squared over R, V squared over R squared in both of these terms, so I can factor that out. Right? And when that comes out of the square root, then I simply just get that this is b squared over r. And then under the square root side, I have a cosine squared theta plus a sine squared theta, which is what?
1.
That's 1, right? Cosine squared theta plus sine squared theta is equal to 1. And so we see that this is equal to b squared over r. So what we've shown is that the magnitude of the acceleration vector is v squared over r. So let me go back to our merry-go-round. Do you have a question? Okay. Good stretch. Okay. So let's go back to our merry-go-round experience. I just want to show you a rather amazing So, I used to take some of my friends to a merry-go-round. I was doing my PhD. We have fun with physics. So let's just, I know, probably very elementary, but I thought it was fun. So I have a merry-go-round here. And this is me holding on for dear life as we're going around. And let's assume that this distance out here is 2 meters. Okay, so this is a fairly large merry-go-round. And let's assume that the time that it takes to go around is, and we'll just call this big T, it means period, is 1 second. So this is going around like this. That seem reasonable? That's actually pretty fast. Yeah, merry-go-round going that fast. But okay, so what is the magnitude of the velocity? What is the magnitude? We're not interested right now in the direction aspect. We're just interested in the magnitude of the velocity. How would I find that? Yes. Okay, good. How do you find the circumference of a circle? 2 pi r. So the velocity is just going to be 2 pi r divided by t. Okay, so it's just the circumference of the circle divided by time. So it's just this length, which is just the length of the circle divided by the time that it takes to go around, undergo that length period. So what is the centripetal acceleration? Al, what is the centripetal acceleration going around there? How would we do that? Yes? Okay, good. So we get 4 pi squared r all over t squared, and I already divided through that by that r. Well, I'll put an r anyway. Okay, so all I did is I just took v squared over r. So you take v, which was pointed out, was 2 pi r over t. I square that, and then that's 4 pi squared r squared over t squared, and then I divide it by the radius again, r. So one of these r's comes out. Okay, so I get 4 pi squared r all over t squared. And just for the sake of this example, we're going to assume that pi squared is 10. Okay, so I get 4 times 10 times the radius, which is 2 meters squared, all over a second, 1 second squared. And we see that we get that this is 4 times 4, which is 100. Oh, sorry, this isn't squared. So we get 80 meters per second squared. So how many G's is that? 8 G's. Anyone ever experienced 8 G's before? You should try it. Right? If 1 G is 10 meters per second squared, and this is 8 G's of acceleration, and you'll pass out. Don't pass out. It's really hard to get a merry-go-round going this fast, so don't worry. But it can be pretty intense. And when we get to conservation of angular momentum, I'll show you why it was fun to take all the friends. So what you can do is you can get more heavy guys on the 4 heavy guys and 1 light guy on the outside. You get it spinning around, and then you have the 4 heavy guys go to the center. And then it's really incredible. Okay, so fun with physics. So I thought that was a little more interesting example. Okay, any questions? Yeah. Sorry? Well, you have to, I'm not sure I understand your question. So, not sure I understand what you mean, but so your body is going to try and get as far out as it possibly can, and in the process of doing this, moving mass away from it will actually slow down the rotation speed. If that's what you mean. Okay, yeah, there is wind resistance, but it's pretty negligible. I don't think that's what you mean, though, right? Okay. Oh, we can talk afterwards. Okay. So, anyway, just it is kind of fun to try this sometime. Okay. Any questions before we move on? All right, so let's do relative motion in 1 dimension, and we'll do it in 2 dimensions. Okay, so now we've always defined an origin as being at this one particular place, but there's no really preferred place. You've all been driving on the highway, and you've seen someone standing on the side of the road, and they're not moving in their rest frame, but in your rest frame, you're moving at the speed of the car, right? And then you see a car pass you. And this car may be going 70 miles an hour relative to the person on the ground, but you may be going 65, so it looks like this car is passing you at 5 miles per hour, right? So what we're asking is, there's a frame in which you think about how the world around you, right? As you're driving a car, you think about the world according to your reference frame, which is in the car. So when that car is passing you at 70 miles per hour, in your reference frame, you see that car passing you at 5 miles per hour if you're going 65. But to the person who's standing on the side of the road, he sees the person going at 70, and he sees you going at 65. And so what we're going to do is we're going to define reference frames. And so we're going to call this what we would call a lab frame or a reference frame, which is the person that's not moving, like the person standing on the side of the road. Okay, so we're going to call this essentially the rest frame. And then we're going to say that there is a moving frame here that's moving with some velocity. Okay, so just like you moving in your car. And then with respect to these 2 reference frames, we're going to have some other object that is moving with respect to this. So what we want to find out is, how is this object moving with respect to this frame and with respect to this frame, and how can we relate these 2 things? Okay, so this is relative motions in 1 dimension. So I've drawn P up here, but it looks like it's a 2-dimensional thing, but we're just really going to consider what happens along the x-axis. We're not going to worry about y for the moment. We will in just a minute. Okay, so this distance, okay, so A, B, and P. Okay, so the displacement of this point P with respect to A is this distance right here, right? With respect to this origin, this has the distance of point B along the x-axis. With respect to B, this is the distance, right? So we have here this distance, and then we also have the distance of A with respect to B. Okay, now let me just make sure I follow the book's notation on this because they have a fairly they like to use a Pico notation. Okay, XPA. So they call this one XPA, which means the distance of P relative to reference point A. And then they call this one XPB. In other words, what is the distance of P with respect to B? And then they have this one as being XBA, which is Alex. So what they have is, I think they call Alex, Bob, and P or whatever. I can't remember who they find it, but Alex, Barbara, and P. So they say Alex is observing Barbara's coordinate system moving at this particular time at a displacement of x. And so this is Alex is observing Barbara's position. Okay? Alex is observing point P, and Barbara is observing point P in her reference frame. So that's what all of these things mean. So now you can see simply that XPA is the sum of XPB plus XPA. So we have XPA is equal to XPB plus XBA. Okay, how do we find the velocities for this equation? Well, what would you expect? Okay, good. I just take the derivative with respect to time. So I say dxpa dt is equal to dxpb dt plus vxba dt. Okay, so I can see that vpa is equal to vpb plus vba. How would I find acceleration? Okay, take the derivative again. So I have A, PA equals A, PB plus, now let's think about this one for a second. What we've assumed here is that this reference frame is moving at a constant speed with respect to this point here. So what is dVBA, dt? 0. Because it's moving, this reference frame is moving at a constant velocity with respect to this one. Okay? So we're going to say that this is 0, and so we can see that APA is equal to ABB. Now, let's think about this for a second. So what we're really doing is we're describing the motion of this particle in two different reference frames. Now this particle, if it starts undergoing acceleration and this is moving at a constant speed, you would expect that the acceleration that this observer sees is going to be the same as the acceleration that this observer sees. And we'll do an example here. So I lived in Europe for a while, and one of my things that I really enjoyed doing was riding the TGV. Has anyone ever ridden the TGV in France? Or the bullet train? go about 300 kilometers per hour. And one of the things that always amazed me is how fast they would go relative to each other. So this train would be a couple hundred meters long and sound like, oh, that was it. You pass it, and it didn't sound like like a regular train. It was incredibly quiet, and then every now and then, oh, now the train passing, a 200 meter long train. And you can begin to understand why, because in we're gonna show this here. So here's a train going along here, and here's another train going along here, and here's an observer here. We'll just say this is Alex, and then this is me. I'll say this is Jay, and then this is P. So this is the train passing here. P. So let's find the velocities of the relative things. So let's say this one is moving 300 kilometers per hour, and this one is moving minus 300 kilometers per hour. Okay? So this is, if they're moving in opposite directions, what would you expect that the velocity is of this train relative to this train? Minus 600 kilometers per hour, right? That's what you expect. So we need to be able to show that mathematically, right? So what we have is V, we have VPA is equal to VPJ, which is just relative to me, plus VJA. Okay? Now, what is VPA? So let me remind you, what we're seeing is this is Alex is observing the velocity of this train. What does he observe? He sees minus 300 kilometers per hour, right? What do I see? Well, I don't know yet. Right? That's what we're trying to find out. What does, how does Alex observe me? At 300, right? So, rather than putting a question mark, I'm just going to call VPJ. And we can see from that that VPJ, I'm just going to bring 300 over to this side. And so we see that VPJ is equal to minus 600 kilometers per hour. So it's moving really, really fast relative to me in this particular train. Okay. So now, if it took 100th of an hour to slow down, so let's say, so I'm going to still be moving at 300 kilometers per hour, but P starts to slow down, right? It's coming to a train station. And so it starts slowing down. So it goes from 300 kilometers, minus 300 kilometers per hour to 0, and we'll just say in 1/100th of an hour, right? So 1/100th, I guess that's about 36 seconds, which would be very fast. So nevertheless, we'll do that. So what is the acceleration of P with respect to A? How do we find that? What is the velocity final? So what we're doing is we're finding the acceleration of that train, which we've labeled as P, with respect to Alex, who is on the sideline or that rest frame, right? Where that's a rest frame where we're considered that to be 0 velocity. So what is the final velocity? 0, right? And then we're going to subtract the initial velocity, which is minus 300 kilometers per hour, over the time that it took, and we'll just say this is 0.01 hours. And so we see that this is 30,000 kilometers per hour squared. Okay? Now, so I've taught the graduate quantum mechanics course for a very, very long time. And I'm not sure if any of you noticed that, but whenever I write H, I put an H bar. And those of you who take the quantum mechanics course, you'll understand why. So if I start making H bars, you'll just know that that is Planck's constant. It has nothing to do with this class. I apologize if I write H bar. Okay, so this is 300 minus 30,000 kilometers per hour squared, which is just an acceleration. Now, how about we're going to call this APJ, right? So I want to find the acceleration of the train with respect to me. What do I see? Well, what is the final velocity of that train? This is a little bit trickier. Now, I'm finding the final velocity with respect to my frame. You've all been have you been in an airplane where suddenly it looks like you've been in a situation where the rest frame, where you thought you were stationary and things start moving relative to you? Right, but it may actually, so I was in an airplane one time, and suddenly I saw something out of my side, my peripheral, that started moving. I thought the airplane was moving, but it was like a truck moving with respect to me. Right, so the airplane wasn't moving, it was the truck moving. So in the rest, I'm actually considering my rest frame, in which I'm moving here at 300 kilometers per hour. So how fast is this moving when in Alex's rest frame this is 0? So I'm going 300 kilometers per hour, but this is moving at 0 now. Right? So let's say this is not moving at all with respect to Alex, but I'm going 300 kilometers per hour. How fast, in my frame, how fast does this look like it's moving? Minus 300. So when it's in rest with respect to Alex, when I look at it, it doesn't look like it's at rest anymore. It looks like it's going at minus 300 kilometers per hour. Right? If I think that I'm moving at 0, or I consider everything in my frame, then what I see is that Alex, that train appears to be going minus 300 miles per hour, even though in Alex's frame, it's just stopped at a station. Right? So its final velocity is minus 300 kilometers per hour. And what is its initial velocity? Minus 600. Right? That's what we were just talking about. It was going relative to me minus 600 kilometers per hour, and it did it in the same amount of time. And so what you can see is I get minus 300 plus 600, and so I get the same thing here. So I get 30,000 kilometers per hour squared. So you just have to remember that the final and initial velocity are different for me, but the difference is the same. Okay? So now let's do motion in relative motion in 2 dimensions. And it's the same thing, but now what we're going to do is we're going to do it vectorially. I have some point P, and what this point P does is, this is, I'm going to assume, is at the rest frame again. This is going to be moving, and it could be moving at some velocity. Okay, so what I'm going to do is I'm going to have an R, B, A, coming from the origin of this to the origin of that. Then I'm going to have an R, P, A, which is the radius or the displacement vector relative to this coordinate up to P. And I'm going to have an R, P, B. Or what is P relative to the origin of this coordinate system? Now you can see, just doing vectors again, how these are related. And we see that R, P, A is equal to R, P, B, plus R, P, A, just as we did before. But now we're doing the vector sum rather than just that linear sum of those components. So similarly, if we take the time derivative, if we we take the derivative of these with respect to time, we see that VPA is equal to VPB, which is plus VPA. And if we take the derivative again, we're assuming that this is going to move at a constant velocity with respect to this. So then we see that APA is equal to APB. It's the same thing as what we did 5 minutes. Yes, good. Time for one exam. And then you guys, I hope you have an awesome, fun weekend. So now we're going to do a quick example. Suppose, so they have this little, I'm a terrible artist. I apologize. Apologize that right now. Okay, we have some airplane that is undergoing motion like this. So what it has is it has a strong wind coming up to the side. So it has a wind that's coming up here, so that it has to tilt its nose because the wind the plane is actually moving like this. So it has to angle its nose because the force of the wind pushing on it sideways is causing it to move along this direction, even though it's pointed this way, because of the fact that there's a wind pointing like this. So let me just read it right straight from the book, and then we'll explain it in terms of these. Okay, a plane moves due east while the pilot points the plane somewhat south of east. So that's what we're describing right there. So the plane is moving due east as the pilot points it southeast. And the plane has a velocity of VPW relative to the wind. So this is the VPW. It's moving with respect to the wind, and it says 215 kilometers per hour, directed at an angle theta south of east. So it's moving along here, theta, south of east. The wind has a velocity of VWG, which is what we're going to, VWG. This is the velocity of the plane with respect to the wind, and this is the velocity of the plane with respect to the ground. Okay. And with the wind speed directed 20 degrees east of north. Okay. So this is, theta here is 20 degrees. This angle is 20 degrees. So what we're doing is we're going 20 degrees east of the north. So we're taking the angle relative to the north direction. And then what we're trying to do is it wants to ask, what is this angle here that it has to tilt the nose in order to do this? And what is the speed that it's moving relative to the ground? Okay, so we can see this pretty straightforwardly, right? Because VPG is simply just a vector sum. VPG is equal to VPW plus VWG. Then we break it up into two components, right? There's a component of this plane that's moving along the x-axis. So we're going to find the VPG is all of its velocity is in this direction. So we don't need to worry about breaking up that up into components. It's only that component. There's no component of VPG in this direction. So we're going to say simply that this is 0. And then we take the components along. So this is along the y-axis. Right, along the y-axis, there is no VPG. Right, the projection is that there's nothing along the y-axis. Then I'm going to take the sine of theta times this VPW, which we said was 215 kilometers per hour. I'm sorry, I'm going quickly. And then I'm going to take VWG, I'm going to break it up into its components. I'm going to have a cosine, which is going to be going along this axis, and then I'm going to have a sine going along this axis. I'm going to take this component plus this component, and that's going to be equal to the plane going along this direction. Right? So basically all we do is break this up into components, and with that we can get both the angle and the ground speed. Okay? So